Hi, my name is Joel. I work here at the Prem Center at UCF, and I'm here today to film Kamal do an experiment with 2D materials.
And I'm Kamal Harrison. I'm also a part of the Prem Center with Cycloconductor, and today we will be investigating the properties of 2D materials using the basic physics principle of capacitance. This is our optical microscope. Beneath our objective, we have our substrate. The image seen through the microscope is projected on the screen here, and on this screen, we see the top-down view of our real-world application of this schematic here. Each of these darker triangles represent our top plate MOS2 that we can see in this diagram here. Each of these electrode leads represent the source and drain that is shown in these yellow boxes here, and that we will use to measure the current flowing through the top plate of our capacitor. This background gray color represents this dielectric blue, and beneath all of this, behind it all, is going to be our heavily doped silicon. Next, I will zoom out. Now that we've zoomed out, we can see our contact pads on either side of our source and drain. We need to use these because the small leads from the source and drain are about 1.5 microns thick. That's pretty thin. The size of a human hair is about 80 microns, so you could imagine how difficult it is to deal with. These much larger contact pads we are going to contact electrically with our experimental setup. This will allow us to measure our source and drain, set a small voltage through it, and correctly measure the current running through it using an ammeter. We have moved our MOS2 device to this microscope. The first thing I'm going to do is attach this metal bracelet, which is connected through metal to this copper plate, which is stuck all the way into the ground. This grounds me since the static charge of my body is much greater than the charges we will be measuring on this device. Here we have our three electrical contacts represented by these 3 metal needles. Up top here we have our source, which will connect to the positive end of our battery. Here is our drain, which will connect to the negative end of our battery. And we will run a small potential here between the source and drain to measure the current from the excess charges on the MOS2. This metal needle is connected to the bottom plate, our heavily doped silicon, through this copper puck and through the electrical tape. We will change the voltage on the bottom plate with this needle, and we will experience charge collecting on the MOS2, which we will measure using the source and drain. We have a voltage difference between the top and bottom plate of our capacitor. This will induce a charge on the top plate, which is the MOS2 that we will be measuring. Using an additional voltage source through the source and drain, we can measure the current running through of our top plate. We'll measure this using an ammeter, but not this ammeter. This one's too old. We have a computer program that will measure the current through the source and drain. As we increase the voltage difference between the top and bottom plate, we will increase the amount of charges on our top plate on our MOS2, which will increase the current through the source and drain. Now we will run our experiment. On our y-axis, we will have the output current between the source and drain. On our x-axis, we will have the voltage difference we are putting between the bottom and top plate. As we begin, we see a small amount of current. This is due to a small amount of charge on the top plate. As the voltage increases, we will see more charge on the top plate, which equates to more current running through the system. As you can see, when the voltage between the bottom and top plate increases, our current also increases through the source and drain due to the charges formed on the MOS2.